Alright, why didn't I move the light like I did before? But here we go. It's looking better now. Okay, so we want to look at this scenario where we've got acid and base, strong acid, strong base to form a salt and water. So if we start with scenario 1, which is that we have zero point 0.1 molar, I think it is, yep, of HCl, and we have 25 milliliters of that. And then we have 0.1 molar of sodium hydroxide, and we're only going to add 10 milliliters of that. We want to figure out what is the resulting pH from this. So what we have is we can calculate our number of moles of each thing. So the number of moles of, let's say, of hydrochloric acid in 25 milliliters that gives us 2.5 moles of hydrochloric acid. If we do the same calculation for sodium hydroxide, we find that we get 2.5 times 10 to the minus 3 moles of HCl, and 1.0 times 10 to the minus 3 moles of sodium hydroxide. Okay, time for an ice table. Ice table is going to be, so we have HCl plus NaOH gives us a salt and water. Initially, we're going to put in moles instead of concentration. Initially, we have 2.5 times 10 to the minus 3 moles of HCl, and we have 1.0 times 10 to the minus 3 moles of sodium hydroxide. And we have none of these. The change is all of the sodium hydroxide is going to be consumed. Or at least we're looking at consumption of sodium hydroxide. So that's going to be, so all of it's going to be consumed. So the change is going to be minus 1.0 times 10 to the minus 3 . And then we end up with plus. We're not concerned about this really, but for, completion, this is supposed to be a plus. We subtract, and at equilibrium, we have 1.5 times 10 to the minus 3 moles of HCl that's left over, and we have 0 moles of NaOH. So this is what we're going to use to figure out our pH of our system. So in order to figure out the pH of our system, we need the concentration of H+. And we know that if we were to write a dissociation reaction for HCl, it would be H plus Cl minus. So we know that for H plus concentration, it's going to be probably these number of moles, 1.5 times 10 to the minus 3 moles and then it's going to be over some volume. So some volume of water. How do we know how much volume? Well, the total volume of solution is the 25 milliliters of HCl plus the 10 milliliters of NaOH. So if we add these together, we have a total of 35 milliliters of solution. So to figure out our proton concentration, we are going to insert 35 milliliters here. So let's go. H plus is equal to 1.5 times 10 to the minus 3 moles all over 35 milliliters. Convert milliliters to liters. And then we're going to have a molarity of protons. And that number, I think I have on hand, is 0.0429 molar. Once we have the concentration, to get the pH, all we have to do is take the negative log of this value, because we take the negative log of H plus. So negative log of 0.429 is equal to a pH of 1.37. So after this titration of strong acid with strong acid and strong base, we find that we get a pH at the end of 1.37. So we're still really high. We haven't reached the equivalence point. So like when we were talking about the equivalence point here, we're still down here in that area. We haven't gotten up higher. And so that's how this shows all of the sodium hydroxide gets consumed. What's left over is some number of moles of HCl. We figured out that. Then we took the total volume of the solution, which is 35, the 25 of the HCl, plus the 10 milliliters of the NaOH to get 35 milliliters. And then we calculated the molarity, which would be the H plus, because we know that this fully dissociates. This is 1.5 times 10 to the minus 3. This becomes 0, and then we just get H plus and Cl minus, like we've been doing for all of our acid-base reactions, and to then solve for our pH to be 1.37. Okay, now let's look at if we had the same amount. So we're just going to change a few things. If we have the same amount of sodium hydroxide instead, we have 25 milliliters, then that changes our amount of sodium hydroxide that we have here to the number of moles. The number of moles then becomes 2.5. So we change this. This is scenario 2. What if we add equal amounts of acid and base? If we add equal amounts of acid and base, we calculate the number of moles for each of those. Those end up being equal also. So that means that when we put this into our ice table, we start initially with 2.5 times 10 to the minus 3, right? And then that means that all of the sodium hydroxide is going to be consumed. And it's going to go to products. So if all of it is consumed, again, we're left with 0 here and 0 here. And 0, hold on a second, let me think about that. Oh, it doesn't undergo hydrolysis, that's right. So we are basically at the equivalence point. We have an equal number of protons to hydroxide ions. And we didn't talk a lot about that because in chapter 6 there was some discussion on what is going to undergo hydrolysis, salts that are going to undergo hydrolysis. I know that those questions are in your homework, so we can answer those in class on Monday. But what happens is when you add two equal amounts of a strong acid and a strong base, you end up at the equivalence point. You have an equal number of protons and OH, and it does not undergo hydrolysis because there's nothing left over. Since that is the case, then that means that our pH is if this is equal, we know that our pH off the bat is equal to 7, and we also know that the concentration of each of these is 1 times 10 to the minus 7. And we learned that in class when we were talking about chapter 16. So this is at the equivalence point. Which would be right there in the very center. pH is 7, everything's balanced. Okay, great. Now let's look at scenario 3, where we add even more base. Scenario 3 is where we add instead 35 milliliters of NaOH. So let's change this. 35 milliliters. That means that we will not be at the equivalence point. We probably will be very basic because we would have an excess of base. Let's change this to 35. And let's change this to 3.5, which means that we will change these to 3.5. So now what's going to happen is all of the HCl is going to be consumed because that is now our limiting reactant. So we subtract 2.5 times 10 to the minus 3. We would add 2.5 times 10 to the minus 3, but we don't care about that right now because we're looking for pH. This becomes 0, and then this becomes 1.5 times 10 to the minus 3. Now, we want to figure out pH. In order to figure out pH, we're going to start with pOH because we have an excess of base. So let's go over here and look. Before we had an excess of acid. Now we have an excess of base. So we have NaOH that is still dissociated to form Na plus and OH minus, right? So that means that we have 1.5 times 10 to the minus 3 moles, and this is of OH. This is of OH concentration of hydroxides because that's what dissociates from this 1.5 here. in order to get concentration, we need to know volume, right? And so volume, the total volume of solution is 25 plus 35 now, which makes the total volume of the solution 60 milliliters. So then to figure out the pOH, so let me just say that this is what we're trying to figure out. In order to figure out the pOH is what it's going to be, we change this to 60, right? We divide, and then we get a value of 0. Wait a second. Oh, not 1.5. Sorry, this is 1. Right. Subtract. We get 1. We get 1. 1 divided by 60 is equal to 0.0167 molar. So now we figure out a pOH, which is the negative log of 0.0167. That gives us a value of 1.78. In order to find the pH, then it's going to be 14 minus this pOH, which is 1.78, to then give us a pH of 12.22. And that makes sense because we have an excess of base. And so that's how we figure out our pH of after doing a titration of a strong acid and a strong base.